Hey, how's it going? This is going to be our first video lecture. Today we're going to learn about limits. So probably some of you have some background in limits. You probably studied them in pre-calc in Snyder or Cridge last year, but we're going to talk about them a little bit more formally. Because without limits, we really wouldn't have calculus as we know it. But as important as they are, we're not going to spend tons and tons of time on them. But you should have an idea of what it means to take a limit, the limiting process. You should be able to evaluate some simple limits algebraically or graphically. And then hopefully when this is all over, you're going to understand why limits are important to calculus. So basically there are two types of limits that we're going to talk about. The limit at a point and the limit at infinity. Okay, we'll spend more time later on the infinite limits, but we're going to talk mainly about limits at a point right now. So let's just jump in here and give you a formal definition of limit. Let's see, what color do you want? Let's go blue. So our formal definition of limit, actually I should say this is our informal definition of limit. Down the road we'll give you something that's very, very formal, that's kind of crazy and intimidating, but today we're going to learn this informal definition. So L is the limit of f, a function f, as x approaches, if I could spell approaches, c, if and only if. Okay, by the way, that IFF there means if and only if. That's our abbreviation for that. L is the limit of f as x approaches c, if and only if. L is the one number f gets close to, and then I'm going to put in parentheses here, but not necessarily equal to, L is the one number f gets close to, but not necessarily equal to, as x gets close to, but not necessarily equal to. C. Okay, so this is our informal definition of limit. L is the one number f gets close to, but not necessarily equal to, as x gets close to, but not necessarily equal to c. Okay, now remember, f's are your y values, and x's are on the x-axis. X is approaching c, and then f is your y values. Okay, notation for a limit, and this is probably what you've seen before, and you're probably familiar with this. You've seen this notation. It would look like this: the limit as x goes to c of f of x equals L. So that's the notation. This is the notation that we're going to use when we're representing a limit. So I think this definition is going to make the most sense if we start looking at some pictures. So let's look at some pictures and see what we see. Remember, the one number f gets close to, but not necessarily equal to, as x gets close to, but not necessarily equal to c. Okay, so I'm going to draw some pictures here. Alright, so I'm just going to draw some pictures of some graphs. Okay, so here we go. Ready? So I'm going to say this is we're going to use the same numbers here. We'll say this is 2, and that's 5. We use a lot of these same numbers, so the graphs are easy for you to sketch. Okay, so here's our function. Looks nice. Okay, then we'll call this function f. Hello, f. And I'm going to ask you this. Does this function f have a limit as x goes to 2? So we look at these y values. We say, okay, okay, as x gets close to 2, what are the y values getting close to? Well, they appear to be getting close to 5, and they always seem to be getting close to 5, no matter which way I go to 2. So this limit is 5. And so if you think back to that definition, when we said f gets close to, but not necessarily equal to, 5. See, f doesn't equal 5 there. In fact, what is f of 5? I'm sorry, what is f of 2? Is it 5? No, it does not exist. Okay? But that doesn't matter. The limit is still 5. Okay? Let's try another one. Same numbers here. Put another number there. Okay. So hopefully my head's out of the way there. I'll step out of the way so you can get a view of that graph. Okay, so this is where still call him f. Hello, f. All right, now, whoops. So let's see. What's the limit as x goes to 2 of this function? Well, what happens to the y values of this function as x approaches 2? So we jump on this curve. The y values seem to be approaching what? 5. Right? There's one number the y values seem to be approaching. But what's f of 2? F of 2 is actually 3. But the limit is still 5 because the values of the function are approaching 5. It just happens to be at 2, they equal 3. So this is what we mean by when we say f gets close to, but not necessarily equal to. Because in this case, f of 2 is 3, but the y values were approaching 5. Okay? Let's make another example. We'll do this one over here. Okay, let's see. All right, let's do orange this time. All right, so we got that nice graph. Here we go. Ready? Say this is 3, and that's 5. So now I'm asking you, what's the limit as x goes to 2 of this function? Call him f again. Okay, now, is there one number that f is getting close to? Well, if you look at the left side of 2, over here, it's approaching 5. On the right side of 2, it's approaching 2. There is not one number that f's getting close to. There's 2 different values that this function is approaching. So we say this limit, just like the movie, the limit does not exist. Okay? But in this case, what does f of 2 equal? Well, if you look very carefully, f of 2 does equal 5. Okay? And that's okay. Okay? The limit and the function value don't have to equal each other. And same thing here. This was okay. That's one of the big misconceptions when we're talking about limits, particularly graphically, is that students often think that the limit and the function value have to be the same, but they don't necessarily. That goes back to that definition, but not necessarily equal to. Let's look at one more picture. one more picture. Let's see. Here we go. Another graph. I don't know if you guys can hear that squeak. All right. So there's our picture. Hello, F. We'll call him F. And now I'm asking you, what's the limit as x goes to 2 here? And is there one number that f seems to be getting close to? Yeah, there is. In fact, if you jump on this curve and you approach 2 from both sides, they're approaching 7. And it turns out f of 2 equals 7. You guys see that? That this is the case where the limit and the function value are the same. And if you notice something really, really kind of peculiar about this particular graph as compared to the other 3 graphs that we've drawn, maybe you see it. If you were sitting in front of me, we would have this big aha moment where I would say, hey, what do you notice about this graph as compared to the other 3 graphs that we looked at? And you would talk and you would say, hey, this one right here was continuous. That graph right there is continuous. All 3 of the other ones were not continuous. If you remember back in Algebra 2, or maybe pre-calc, somewhere along the way you learned the definition of continuity is that you can draw the graph without picking up your pencil. Well, this one, you had to pick up your pencil, right? This one was not continuous. The other 2 that we had, couldn't draw without picking up your pencil. But this one right here, you can draw without picking up your pencil. And it turns out that idea of being able to draw a graph without picking up your pencil is the informal definition of continuity. But now we could probably come up with a more formal definition of continuity in the context of limit. So what does it mean for a function to be continuous in the context of a limit? So let's see here. Let's see if we can come up with that definition. So continuity at a point. Continuity at a point. So here we go. A function is continuous at x equals c if and only if there are 3 things stupid. There are 3 things that have to be true in order for a function to be continuous at x equals c. Okay? So why don't you pause this video and see if you can answer these questions. Pause your video and see if you can fill in what 3 things have to be true in order for a function to be continuous at x equals c. We'll come back in a second and you can answer. Now before you hit pause, think that in order for things to be equal, they have to exist first. So think through that, pause the video, and come back, and then we'll see if you're right. Okay, so here we go. Maybe you paused, maybe you didn't. Maybe you're lazy and you just wanted to listen for the answer. I get it. Sometimes we're all that way. But here we go. A function is continuous with x equals c if and only if, first thing, f of c has to exist. What does that mean? That means, like, in your graph or in your function, in your picture, you've got a dot there. There's a value for the function at x equals c. Number 2, the limit as x goes to c of the function has to exist. So what does that mean? Well, that means if your limit exists, that means you can't have something that looks like this. See, here's an example of a function who f of c exists, like that value right there has a dot, but the limit doesn't exist. Okay, and then the third thing is for there to be continuity at a point is these 2 things here have to be equal. The limit as x goes to c of f of x equals f of c. Okay? And what most students come up with when they're doing this for the first time and they see this for the first time, they know this is what has to happen, but they just don't think that they had to say those two things also. But technically speaking, you have to exist before you can equal something else. So I know that's being kind of nitpicky, but it is what it is. Okay, let's do an example. We're going to do two examples. We're going to do some limit calculations with a graph, and then we're going to do some limit calculations from a table. The next video that we do, we'll look at doing some limits algebraically. Those tend to be the hardest. Shouldn't use that word. Those tend to be the ones that provide the biggest challenge. How does that sound? I like that. Okay, you ready? So I'm going to draw a nice big graph here. Draw it over here. Okay, let's see. I'm going to draw. I got some notes over here for myself just so I don't stand here and look like an idiot. I can do that pretty easily on my own. So I put that there, and then I'm going to put this here. Go up here to this. 1 and 3. Okay, so this is my function f. Okay, so we've got there's a dot there, a hole there. These are called removable discontinuities there, if you remember from your Algebra 2 days. These are called step discontinuities, in case you were wondering. I didn't give you a value here, but this is x equals 4 there. It looks like we got some sort of vertical asymptote going on there. Okay. So here we go. Ready? First question. I'm going to get out of the way here. My first question for this graph, hopefully you have it copied by now, is what's the limit as x goes to -1? And I'm going to do this just to add a new little twist to this. I'm going to say what's the limit as x goes to -1, and then I'm going to put a little minus sign up there. Now what does that little minus sign up there mean? The limit as x goes to -1, that right there means from the left. Okay? So when we say from the left or from the right, we're just talking about, hey, what if we just approach from the one side? So that definition where we say the one number f gets close to, you're really just going to approach from one side. So if I'm looking at as x goes to -1 from the left side, it looks like we're approaching something right there, right? I didn't give you a value, so let's give that a value. Let's say it's 4, okay? And now similarly, can you tell me what's the limit as x goes to 1? And then I put a plus sign. That means from the right. And let's give that a value there. How about we say that's 2? And while we're at it, we probably should put a value up here for this guy. Let's say that's 7. Okay? So what's the limit as x goes to 1 from the right? -1 from the right? Sorry. -2. That's not -2, +2. Okay? So I've got the limit as x goes to -1 from the left is 4. The limit as x goes to -1 from the right is 2. But now, if I just straight up ask you for the limit as x goes to -1, and I don't indicate right or left, the implication there is that you're going to look at right and left together. Uh-oh. Uh-oh. Okay, they don't go to the same thing. So in this particular example, there's not one number they're going to. The limit does not exist. Okay? So we've got the limit as x goes to -1 from the left, from the right, and then in general. Thank you. All right, so let's do another one. Let's try the limit as x goes to 3. What do you think the limit as x goes to 3 of this function is. So take a second, think about that. Well, is there one number that f is getting close to, but not necessarily equal to? Yeah, there is. It would be 7. In fact, if there happened to be a dot, like right there, like let's say that f of 3 equaled 5, that limit would still be 7. Okay? And then lastly, let's do one more. How about this one? Hopefully you can see this over my belly here. The limit as x goes to 4. The limit as x goes to 4. So what's happening at x equals 4? Well, this function is taking off to negative infinity, right? So there are two sort of accepted answers here, and I feel like it's getting more and more accepted to just say that this answer is negative infinity. Now there are some sticklers out there that would say that this limit doesn't exist. The limit is infinite, but negative infinity is a perfect answer to say there. Okay? Now, one of the things that I might ask you to think about down the road is how does a function, what's going to cause a function to approach negative infinity or positive infinity? What might cause that to happen? How would your function be defined? What might it look like in order for the thing to take off to infinity or to take off to negative infinity? Certainly if it was a polynomial, like, x squared plus 3x plus 5, and let's even add another term on there, x cubed. If it were a polynomial function, that would take off to infinity or negative infinity on the ends. I mean, you guys probably learned the whole, end behavior. But what would cause a function at x equals 4 to take off to a negative infinity or positive infinity? What would cause that to happen? So I want you to be thinking about that over the next day or so, because we'll be getting back to that. So if this were a class, I would say, do you have any questions on this? And you probably raise your hand, and I would say, oh yeah, what's your question? And you would have, but we can't do that. I mean, this is just is. So hopefully if you do have questions, make notes of them, and then reach out to me and say, hey, Mitter, I don't understand what that meant, or I don't understand what that dot, why do you have that dot there? Ask me questions, because that's the only way this is going to work. Let's do another one. This is going to be not a graphical one, but a one from a table, and we're going to use some technology, some Desmos. So hopefully you can access the Desmos tab on your Chromebook. Okay, so I forget what my example was that I made up, so I'm going to look at my cheat sheet here. Okay, here we go. This actually is going to maybe give you some insight, possibly, into what I was just asking you before. How would a function approach infinity or negative infinity at x equals 4 or 2 or whatever? So here we go. I'm going to just give you this problem right here. The limit as x goes to 2 of 1 minus 2 over x over x squared minus 4. Okay, so here instead of putting f of x, I'm actually just putting in an expression there, and we're going to compute this limit. Okay, now I'm going to tell you right now, your temptation for someone who doesn't know and is still new to learning limits, your temptation, and it's a natural temptation to want to do this, your temptation is going to be like, oh, I got this, I can plug in 2. I'm going to say, oh, if I plug in 2 in the numerator, I get 1 minus 2 over 2, which is 1 minus 1, that's 0. And then in the denominator, 2 squared minus 4, that's 0. So it's 0 over 0. What is 0 over 0? Is it 1? I don't think so. 0 over 0 is actually a fancy word. It's what we call indeterminate. And we'll learn more about this word down the road, but it's indeterminate. 0 over 0 does not equal 1. It does not equal 2. It's indeterminate. In fact, it might equal something different depending on what the problem is or what the limiting situation is. In fact, you're going to see here, it doesn't equal 1. It equals something else. But we're going to figure out what that is. All right. So we could try to sketch a graph of this function and see what's happening as x goes to 2. Or we could look at a table, because there's different ways of looking at limits. So we're going to do this by looking at a table. Taking a drink of coffee here, even though it is right in the middle of the afternoon. So I'm going to see if I can do this. Okay, so here we go. I'm going to move my face out of the way here. And so if you see on the screen there, okay, I've got a Desmos window open. I have a Desmos window open. And right here in the y equals, I've typed f of x equals, and I put my expression. Okay, so that's something that you know, anytime you're using Desmos, I would get in the habit of just typing in f of x or g of x or h of x, naming the function that you're working with in Desmos, because once it's named, you can use it for all kinds of other stuff. Okay, so go ahead and name it in there. F of x equals 1 minus 2 over x squared minus 4. And then we're going to insert a table here. So in case you don't know how to do that, you click this button right here, and then you go down to Insert Table. So click that underneath in your second line, and then you'll have a table. Now, if you notice, your table, probably when you do this, right here, your table probably says y1 there. And when your table says y1, we don't want it to be y1, we want it to be f. We want to use that function that we've just defined. So what I typed here was f of x1, which is the column right here. And then what I literally did was I just typed in some numbers. I typed in what happens as x approaches 2. So I typed in 1.9. And then I typed in 1.99, 1.999, 1.99999, 1.9999999. Okay? And you keep doing that. And you can see it's looking like 0.125, I think. But remember, I got to check the other side. Because on the, it looks like if I'm plugging in 1.9, 1.99, 1.999, I'm approaching 2 from the left side. What I need to do now is approach 2 from the right side. So now we're going to look at plug in numbers a little bit bigger than 2. So I plugged in, what was it, 2.01. Down here, 2.01, 2.001, 2.00001. And if you keep doing that, you see that it's pretty convincing that the limit is 0.125, or 1/8. Okay? Now, a couple of things that I want to point out here. First of all, the Desmos there is rounding. Okay? It eventually is just calling that 1.125 because it's so close it just rounds it off. Okay? If I actually plugged in 2.0000001, I'm not going to get exactly 1/8. I'm going to get something that's really, really close to 1/8 that Desmos just rounded to 1/8. So make sure that we understand that it's f of 2 here is undefined, right? I mean, we plugged in 2 and we got this nonsense, okay, back here. F of 2 is not 1/8, but f is approaching 1/8 as x approaches 2. Okay? So that's it for our introduction to limits. So hopefully you can read a graph and you can tell me what a limit is from a graph. And hopefully you can calculate a limit from a table by using Desmos. I'm going to make this screen a little bigger here. So you should be able to do now, from your textbook, some problems. I'm going to go ahead and write these here. From section 2.2, I'm going to put these in the classroom too, just to write them down, but some people like to just do this all at once. 46 to 54, 68 to 70, and 82. So can you see all those? It looks like it. So section 2.2 in the book, remember the book is online. If you have issues with accessing that book online, let me know. Also, the answers to odd ones are in the back, and then also in the class Google Drive folder, which we'll talk about when we meet together. There's a document that has all of the worked out solutions to all the odd ones too. So this is in section 2.2. So give those a shot, and we'll talk soon. See ya.